So, okay, so let's move a little bit ahead. So, in the previous class, we were discussing this concept, and we're struggling to. Okay, so as you can see in this diagram, there is this. There are multiple initial states which are marked here in this diagram. Okay, so if you consider that particular thing, then based on that, there should be an arrow over here. Okay, and then considering these two as an initial state, if you start trying to convert it into an end, then this will make sense because the start will be not q naught, then in that case it will be q naught q, and then accordingly you will get these states, and then you will consider q naught q1 q2, and ultimately you get this. Okay, so now let's start a new topic. So here basically what we are trying to realize is how we can use this Erdőn theorem. Okay, so in order to get an equation that represents this entire tangent diagram. Okay, so this is the assumptions. Okay, and based on that we have to formulate some equations, and that equation basically will represent the entire state diagram. So let's first see an example and try to correlate it with the concept later. So let's see one example first. So here what we are saying, consider the transition system and prove that the strings recognized are this entire thing. Okay, this is your tangent diagram, and the task is to prove that this tangent diagram will basically accept this regular solution. Okay, so we try to see any concept which are remaining behind. Okay, so here, so let's derive few equations from this tangent diagram. So simply observe each and every state. Okay, so let's first consider the state Q1. Okay, so we are writing an equation for Q1. Then we are having Q1A. Okay, so basically being in the state Q1, okay, we are traversing in the same state. Okay, with the help of A. My voice is not audible. Hello, is my voice is better than previous?
Yes, sir.
Yes, sir. Okay. So here we are trying to create an equation for the state Q1. So basically we'll observe that which are the arcs which are pointing in Q1. Okay. So one is this your A. Okay. This one pointing in. Another one is this one that is pointing in, and one more that is this one. So three arrows are pointing in Q1. So basically that we can write as Q1A, okay, Q2B, and this empty. Okay, so empty is over here. empty. Okay, so we can write an equation for q1. Likewise, we can write an equation for q2. So observe the pointers pointing in. This is one, this is another, and this is another. So three are there. So q1a, q2b, q2b, q3a. Okay, q3. Likewise for q3 you can write. So there's only one arrow which is pointing in, that is q2a. So we can get these three equations. Okay, and we can basically simplify and do some sort of rearranging, that what we do in our algebra. And the main goal is to derive an equation for this q3. Okay, because q3 is the goal state. Whatever expression get for q3, that will be basically the language which will be accepted by this model. So what is done over here, we have simply rearranged few terms. So q2 is equal to, so we have to get an equation for this q3. So, and q3 is in the form of q2a. Okay, so we have to get what is q2. So for q2 we have to simply simplify the expression. So q2 is equal to q1a, q2b, and q2a. Yeah, q1a plus q2b plus q2a. So basically if you take q2 common, then you will get b plus aa. Okay, and this can be by using Erdős theorem, you can rewrite this thing in this form. Okay, so what is Erdős theorem? Erdős theorem over here, R is equal to QP asterisk. So let me point you to that particular part where it is. That is the only theorem which we are going to use. Okay. So this one, R is equal to Q plus RP, can be rewritten like R is equal to QP asterisk. Okay. So if you have uh, some regular expression in this form, then you can rewrite that expression okay, in this way. Okay, this proof is there, but we have not seen the proof, but we'll take it that it is true. And here, what are the things which you have to consider? Let P and Q be two regular expressions over summation. If P does not contain empty, okay, so if this P does not contain empty, then we can write R is equal to Q plus RP has a unique solution, that is R is equal to QP asterisk. Okay, so that particular thing we will use over here. Where it is. So here, this you can so this q2 can you can consider as R. Okay, this you can consider as q. R is equal to q plus what, q plus R P. So this can be written R is equal to q p asterisk. Okay, so that what we have done over here, this one. Okay. Okay, so after simplifying expression for q2, what we can do, we can substitute q2 in q1. Okay, so we have an equation for q1. So here we are having q2. So as we have got a simplified version of q2, we can substitute that q2 in q1. So q1 is equal to q1a plus. So now instead of q2, what you'll write, you'll write this q1a b plus aa whole asterisk b, that is part of the equation, plus asterisk, it is also part of the equation. So again, you can, what you can do, you can take q1 common and you can simplify things. You will get a plus a, b plus a whole asterisk b plus asterisk. So this is your q1 in terms of q1. Okay, so q1 can be further, this thing can be written like this. Okay, so if you see, if you go through the our identities, then in that case you'll find that this q1 is equal to this entire expression plus empty, can be rewritten like this: q1 is equal to empty and this expression. Okay, so let's see what is that identity. R is equal to this, basically R plus is there. So let us recheck again once again. We can whether it is R asterisk or not. Yeah. So let us. I cannot cut it out. Okay. Let us see. Here, yeah, that is the thing. Hai na? Q1 is there. Q1 is there. That is R is equal to Q1. It is R. Okay. So this entire this you can consider as Q. Okay, maybe Q plus asterisk. So this is Q1 is equal to this whole asterisk. Okay. Maybe somewhere I missed some part. Let me see. So again, we have to. So ultimately, we are applying that identity. Yeah. So let's move, and then after that, simply you can substitute the Q1 into this Q2, and then Q2 can be again substituted in Q3. So you'll get this entire expression. Okay. So Q1, what we get over here, that we can basically insert in this Q2 is equal to Q1A plus Q2B. So everything is in the form of now in Q1. So that can be used. So this we already had, and a Q2 is equal to Q1A. So this Q1 again we get, so that instead of Q1, that part you can put over here, then you'll get. Okay. So Q2 again you had to substitute into Q3, and this, then you'll get expression for Q3. So ultimately we'll get the expression that was desired. So let us go through the theory. So algebraic method using Erdős theorem. So main theorem which we are using is Erdős theorem. So the following method system. So we are having certain assumptions for the transition system. What is that? The transition graph does not have empty moves. It has only one initial state. Its vertices are V1 to Vn. Vi, the regular expression, represents the set of strings accepted by the system even to Vi is a final state. Alpha ij denotes the regular expression representing the set of labels of edge from Vi to Vj. When there is no such edge, then alpha ij is equal to null. So that can basically we can get the following set of equations for V1 to Vn. That is this V1 alpha 1. So this alpha 1 is nothing but your edge label. Okay, so that we were having alpha 2 likewise. So now it will be very kind of clear. By repeatedly applying substitution and theorem this 5.1, we can express Vi in terms of alpha ij's. For getting the set of strings recognizable system, we have to take all the union of all Vi's corresponding to final state. So in the previous example, there was only one final state, so there is no need to do some union and all that. Okay. So yeah. So any doubt? Is it clear this one? Okay. So Mali, there are many questions are there which you can see. Okay. So you can find many questions. So the main thing is you have to know what are the identities and how you can use the Erdős theorem. Okay, and you have to do simple substitution, then you will get an expression. Okay, so let's go through this. Construction of finite automata equivalent to regular expression. Then this method is called subset method. Okay, so here what we have to do, we have to construct automata, finite automata, given regular expression. Okay, so there are two steps are involved. Construct a tangent graph equivalent to the given regular expression using anti-moves. This is done by the theorem 5.2, that is the Erdős theorem, and the transition table for transition graph obtained in step one. Okay, so let us see what is 5.2 so that we can have surety what we are doing. 5.2 theorem. 5.1. Okay, so this we have seen. Okay, removing of empty moves that is basically used in that part. Okay. It is not Erdős theorem, that is removal of empty moves. That we have discussed. We use that. Okay, so let's see. So this is the regular expression which is given, and we have to construct finite automata from this. Okay, so you should definitely try to recognize what is the purpose, from where which part of the string is concatenated and which part of the string and how we are using it, so that you can make sense. So here, first of all, we construct the tangent graph with empty moves using constructions of theorem, that is 5.2. Then we eliminate the empty moves as discussed. We start 5.1.8. So this. Okay, so this entire regular expression you can place between these two states, initial state and final state, because this has to be processed in order to reach to the final state. So we can write that in this manner. And after that we can separate it, as this is nothing but a concatenation of uh, strings. So we can separate these parts, and 0 plus 1 elastic, 0 plus 1 1 0 1 elastic. In order to remove elastic, we can introduce this empty. Okay, so what we are saying over here, we are saying that even if there is no input is provided, we can reach to this state q5. Likewise, from q5 we can move to this q1 even if there is no input is provided. Okay, so that this is how we can remove this epsilon. Okay, as stick. So yeah, and after that, and the same thing we can done for this part also. 0 plus 1 elastic introducing empty, then epsilon will be removed. After that, this 0 plus 1 is nothing but either it is 0 or 1 will remain in q5. So that's what plus is replaced by comma over here. And 0 0 plus 1 1, think that either the input is 0 0 or 1 1, we can reach from q1 to q2. So we are making a path q1 to q7, q7 to q2. Okay, and this will be gone. Likewise for 1 1 also, this should not be there. Yeah. After this, you say apply removal of empty, then get this state. Okay, so simply what you can do, you can this be as V1 and this as V2. Okay, V1. Okay, so you have to review the concept of removal of this. So this will be, the entire thing will be this 2 5. Ultimately, this will be merged. You can say so Q not. So this will have. So this entire thing will be moved. So one by one, you can do considering as states as one and we waiting and doing all that. So let's take. Okay. So this expression you can uh, like DFA. So once you get this, then this trivial. You can do it very easily. Okay, it has to you have to simply write in the form of table. And let's see if there are some. I think maybe here the conversion has been done because there are. This is an simple. You can observe that this is nothing but an NDFA. Okay, so what DFA conversion you can do, then you will get this. Once you get converted, then this is DFA. And here we are doing the reduction. So reduction can be done by the concept of equivalent states. Okay, so here how many states? 3 to 5. Here only 4. Okay, reduced. So yeah, construct DFA. This is regular expression. So this was separated by concatenation. Okay, and then you can remove this zero asterisk by introducing an empty. Okay, so you should see, then you will get it. Okay, there's no such thing. You can convert in table, you can minimize and do all that. So let us see. It's all you can do. Okay, so this is an important concept, pumping lemma. This will discuss when we'll visit a proper example. Okay, so basically you can assume that this is the lemma which can be used to basically verify whether the given language is a particular kind of language or not. Okay, so you'll find that pumping lemma for regular language, pumping lemma for some other language like that, context free language. Okay. So the main goal of this pumping lemma is to basically given a language using this method, one can say that whether that language is the language which it claims. Okay, so we'll see what is pumping lemma theorem and all that. Application of pumping lemma. Okay, so after reviewing the theorem, we will go through this application. Few questions are there based on that. So, like for example, over here, is this is regular or not? Okay, so one can if one can draw a DFA, okay, then definitely it is regular. Okay, or the other way is that you can use pumping lemma, okay, to justify whether this language is regular or not. Okay, so that can be done. So here DFA has been drawn in order to prove that this is regular basically. So a to the power 2n. Okay, so where n is equal to greater than or equal to 1. So if you place n is equal to 1, then you'll get 2 a's, then 2, then 4 a's like that. Okay, so that has been converted into DFA like this. Okay, so when n is equal to 1, 2 a's. So 1a, another a. Okay, reach to the goal state. If it is 2, then 4 a's. So 1a, 2, 3, 4. Okay, like that it will go. So yeah, is this is making sense? This diagram, everyone is clear with this one? Hello.
Yes, sir.
Okay. So let us see if you regular sets and regular grammars. Okay. Okay. So we'll review these concepts. Okay. Today, let us start a new thing. Context-free languages. Okay. So basically, what you should do is that you should try to do more and more questions. Okay. Which we are not able to do it right now because there are many concepts are left that we have to cover. Then I can be assured that we have covered the syllabus. So here, this is another. If you remember what type it is, some if so, what are the types we are having? Type zero, type one, type two. Okay, zero, one, two, three. So what is type three? Type three is regular language. Okay, regular language. What is type two? If somebody remembers, what is type one? There are two are there. One is called as regular. Sorry, one is called as context sensitive language. Another is called as context free language. Okay, so if you simply see what is the form over here, this is it. So let we call the definition context free grammar. G is a context free if every production is the form A tends to alpha, where A belongs to Vn and summation belongs to Vn union summation holistic. Okay, so this is the definition for context free language. So here the main focus is on that context free languages. Okay, so basically this is used to parsing the productions, and we can identify whether it has any kind of ambiguity or not. Okay, so that can be done with the help of this. So construct a context free grammar G, all strings with sign. Okay, so all integers with sign. So here we know that we have these numbers 0 to 9. So summation should be clear. What is summation? These are nothing but terminals. Along with that, we are including this plus and minus. Okay, so that we can generate all integers. And what is vn? Set of variables. So s is the start symbol, sign, that is your plus minus. These are your variables. Digits is 0 to 9. Okay, and then here we are saying integer, that will represent that the number integer. So vn, we are having variables, set of terminals, production rules, and s is the start symbol. So here p consists of. So this is the rule. Okay, so what is the rule? First, s implies. So we know that how we can construct an integer. Okay, so it must have an sign first and then integer. Okay, and then further we can broke this sign into plus minus. Either sign can take plus or it can take minus. Integer can take digit. Okay, an integer. Okay, so you can further resubstitute this one and you can generate. And this is basically a two-digit integer, you can say. Okay, not two digits. So basically here either it can be digit or digit integer. Okay, so if it is single digit, then applying the rule, this rule only once, you'll get a single number. Okay, by applying this rule, this one, this part. And if you want two digit, let's suppose, then you have to apply this two times and then replace this integer by digit and you'll get two digit number. Likewise, you can do it. So basically digit can be replaced by this numbers 0, 1, 2, 3 up to 9. What is L of G? The set of all the integers. For example, the derivation of minus 17 can be as follows. So this is one instance which has been shown for minus 17. So first you'll apply as implies sign integer. Then this sign is basically the negation, negative. This integer, okay, this integer can be replaced by digit integer rule we are having over here. इतना लाल हो गया, दिख ही नहीं रहा है क्या है. So you can apply this rule. Okay, so integer can be replaced by this digit integer, and then this digit and can be replaced by 1, and this and then integer can be replaced by digit, and digit can be replaced by 7. So you'll get this minus 1 7. So this is how, as you can see, is the grammar basically. Okay, for producing all the integers. So this is gem. Okay, so using this rule, you can generate any integer. Okay, so what is uh, okay, so let us see. Here the thing to observe is that we are writing in context free grammar. Okay, so it has to be always in the form of a implies alpha. Okay, where a is nothing but your variable vn, and this summation is your vn union summation whole asterisk. Okay, means what? On the left hand side we'll have always a single variable, and on the right hand side we can have combination of variable and terminal. Okay, including empty. So we can have some sort of like this, a tends to empty, this is allowed. We can write like this, or you can write a implies some, like suppose b and a something like this. This is also allowed. Okay, a b, okay, something like that. This is also allowed. So these are few things. So now it should be clear why what is this vn union summation holistic. Okay, so you can take any possible combination of this union and union, and that can be on the right hand side, and on the left hand side you will have only a single variable. Okay, that is your what free context free grammar. Okay, so that is applied over here in this particular case. On the left hand side you're having a single variable, on the right hand side you are having combination of that. So here we are having only variables. Okay, and here you can see only terminals, here only variables, and here terminals. So here we are not using that combination, but here uh, using only either terminals or variables is sufficient enough. So yeah, that's what it is. Okay, this is one example. And then derivation tree. So basically this tree is used to represent the grammar. Okay, and it is used for parsing purposes. Parsing means basically given the grammar, okay, given the production, you can represent it in a tree like structure, and you can perform. Okay, so there are many things which we have to learn from the tree structure, like what it is, what is this yield of the tree. Okay, what kind of output we are getting from the grammar. Okay, so we'll see few examples, then it will be very much clear that what is the purpose of this tree. So the tree is called as derivation tree. The derivation in a context free grammar can be represented using trees. Okay, so the derivation of the grammar we can represent in the form of tree. Okay, such trees representing derivations are called derivation trees. So this is the definition, formal definition. A derivation tree is also called as parse tree. For a context-free grammar, G, V and summation P comma S is a tree satisfying the following condition. Okay, so what is a derivation tree? You can simply go through this and we can say that that is the derivation tree. So this assumption it has to satisfy. So every vertex has a label, which is a variable or a terminal or empty. Okay, so every vertex in a tree, either it is a variable or terminal or it is empty. The root has a label S, so we cannot have anything else in the root. It will be always S. Okay. Yeah, every vertex has a label. So this is a vertex and it has a label S. The label of an internal vertex is a variable. So always, okay, so if it is an internal, okay, vertex, something like this, so it has to be a variable. Okay, we cannot have terminal if it is an internal vertex. Okay, so we'll see example that in here. If the vertices n1, n2 up to nk written with the labels x1, x2 up to xk are the sons of vertex n with the label A, then this production is the production in P. Okay, so we'll see this is in working and it will be very much clear. The vertex n is a leaf if it is a belongs to submission. Okay, if it is a terminal, then it has to be leaf or empty. N is the only son of its father, its label is empty. So this is an example which is given. So this is production. S implies AAS or A or SS. A implies SBA, BA. So yeah. So by okay, I'm not saying capital A, small a, all that. It is visible. है ना? So this is one example of derivation tree. Given this production, okay, S implies AAS, A and SS. A implies SBA, BA. So here we are specifically applying, for a particular yield over here. Okay, so what options we are having? S. So we are having two options. We are having three options for an S. What is that? One is your S implies A S. This option we can apply, or we can apply S implies A, or we can apply S implies SS. Okay. So in this case, first S is implies SS. This is used, this one, in order to get this part. Okay. And then can substitute by an A. This is applied on that this S, and on this S, AAS is applied, this one. And then on A, we are having two possible options. A tends to SBA and BA. So A tends to BA is applied and S tends to A is applied. So ultimately what you get at the end is yield, okay, the output from the tree. Okay, so that can be traced like this. Okay, so here we are having A, then A, B, A. So from left to right we're moving. So it is a convention that we use. Okay, so from left to right we have to move. So what I says 4, 6 are sons of, so sons and all this is basically successor, and all this is when you can simply understand. So so on the right hand side, whatever we have is nothing but the successor on the left hand side. Okay, or the other name is that this is son and that is father or something like that. Okay, so it is obvious. Okay, so this SS is nothing but son of S. This A is son of, like that. That is written over here. So ordering of leaves from the left. Okay, so that what we have to do. We have to always consider from the left to right. Okay, so we can order all the vertices of a tree in the following way. That is this entire thing. So the important thing is the yield. That what I was talking about. The yield of a derivation tree is the concatenation of the labels of the leaves without repetition of in the left to right ordering. Okay, and the yield of the derivation tree is AABA. Okay, so that is this yield. Okay. So yeah, many definitions are there. So a subtree, a subtree is a subtree of derivation tree. T is a tree whose root has some vertex V of T, whose vertices are descendants of V together with the labels, and whose edges are those connecting the descendants of V. Okay, so this is a so this is a tree you can consider, and this is a subtree. Okay. So what we have taken this part, and we call it as subtree. That's what it is. Okay, कोई सा part ले लो and then subtree. Okay, so what else? Okay, so we'll see if you moves over here. Okay, so this is the question. Consider gamma G whose production are this production is given, and so that S implies this A, construct derivation tree whose yield is this. So basically we have to show that starting from the start symbol S, we can derive this uh, terminal string. Yeah. So that can be done basically. So this production is given, then you can simply try what possible options we are having, and then whether we can reach to this terminal state or not. Okay. So that's what has been stated. And derivation tree for that particular derivation can be drawn like this. So as it implies AAS, so AAS. So firstly that, and then this A is replaced by this SBA. Okay, so is replaced by SBA, and then A. Let us see what is replaced. A is replaced by BA. Okay, as A is replaced by BA. So A is replaced by BA. You can see, and then S at the end is replaced by NA. Okay, so you will get the yield A, B, B, A. Okay, starting from the left to traverse. Okay, so A, this will pick, this will pick, this one, this one, this one. That will be your yield from the derivation tree. Okay, so this is the derivation, and once you know the derivation, you get the derivation, you can represent in the form of tree. Okay, but and how you will get to this terminal string? For that, you have to intuitively apply your intuition that on what which production you have to choose from the set of production so that you can get this. Okay, so that you have to see. Okay, and there are few more definitions are there, like leftmost derivation and rightmost derivation. Okay, so leftmost derivation means always you'll replace the leftmost variable. Okay, while you're deriving, you'll always replace the leftmost variable. Okay, if we have like AAS is there, so leftmost is this A, and then what is leftmost? This A. What is leftmost? This A. So whenever you are replacing, you'll always replace the leftmost variable. Then it will be leftmost what derivation. And at every step of the derivation, if you replace the rightmost variable, then it will be rightmost derivation. Okay, so that's what it is. So means basically we can derive a terminal string either using leftmost derivation or using rightmost derivation. You have to be consistent while you are replacing your variables with terminals. Okay, so let us see. Okay, so this is question. Grammar is given for the string this. Find the leftmost derivation and the rightmost derivation. Okay, so production is given to you, and you have been told to produce this terminal string using leftmost derivation and rightmost derivation. Previously, it was we have not mentioned whether this is leftmost or rightmost. Simply we have replaced in whichever way we want. But here it is asked that we have to derive it by leftmost derivation, rightmost derivation. So if you observe, so we have to get this 0 0 0 1 1 0 1 0 1. Okay, so this thing we have to get. So you can pick a production from this set of productions, and you can apply. Ultimately, you have to give. So here, if you observe, 0B S implies 0B, and B is replaced by what? 0BB. Okay, so I will only mark what the variable which is replaced. Okay, so here this will be replaced, this will be replaced, this will be replaced. So this is basically leftmost derivation. Okay, this is leftmost derivation. So in this particular, if you focus on this, so there are two B's are there, but we are only choosing this leftmost B to get replaced. And this that is how you can identify. Okay, in this case, if you see, then this B is the leftmost because there is no B's anymore. This is the leftmost as well as the rightmost also, but here our concern is the leftmost, so we can replace that. Likewise in this case also. Okay, so yeah, so this is the leftmost and this is the rightmost. So in this case also 0B, this is the leftmost as well as the rightmost, but here the purpose is to apply rightmost, we'll apply right. So as you can see, in the step is replaced by one S. Okay, rightmost. Next step, this S will be replaced by what? By zero b. Okay, this zero b we are getting. So, and again the left right this rightmost b, that is 1s. Okay, and this 1s, and this s is replaced by zero b again, and this b is replaced by 1, and after that only this last b will be replaced by 1. Okay, so this is your leftmost derivation, and this is your rightmost derivation. Okay, and this is the tree which you'll get. Okay, so the derivation tree yield, so derivation tree. Okay, so either you apply leftmost derivation or rightmost derivation, you'll get this same tree. Okay, you'll not get any other tree, because ultimately it has to be replaced by the terminal string. Okay, which, so here that concept can be used in order to basically talk about the ambiguity. Okay, ambiguity is basically, if you, everybody knows, this example is given in book selected information is given. Okay, so there is no comma or anything like that on which term we are focusing. In books selected information is given, so we can have multiple interpretation of that thing. The word selected may refer to books or information. Okay, so whether we are associating selected with this, in book selected information is given, or you are associating that selected to information. Okay, so what you are trying to do, that is the question, ambiguity over here. Okay, so it can be passed in two different ways. So a terminal string w belongs to L of G is ambiguous, so we can say that the grammar is ambiguous basically if there exists two or more derivation trees of w. Okay, so if somebody can show that for a particular string we have more than, okay, more than one, that is two or more derivation tree, if we can show, okay, either there has to be leftmost or rightmost, then we can say that that is your grammar is ambiguous. So this is example. Consider example G. So this is the G. P consists of this production set of production, and for we have two derivation tree for a plus a asterisk b. Okay, so that we can get a plus a asterisk b. Okay, from here also, and from here also we'll get a plus a asterisk b. Okay, so basically what we are saying, whether we are doing the first, okay, which one we are doing associating first, whether we are doing this operation first or we are doing this operation first. There are two ways to interpret the same thing. Okay, that's why this grammar is ambiguous. This, okay, so we don't want that. Okay, so let's conclude for today's class. Try to review the concepts which we have discussed in this class, and yeah, we'll revisit. So on the second half, okay, we'll revisit this thing, and if you have any questions or anything, we'll discuss. And let's see if somebody has prepared any presentation for your QI class. Okay, so let's wind today's class. Any doubts, anyone? Any questions?